Welcome to this explainer. Today, we're pulling back the curtain on something you might think is just a boring math rule, but it's actually the hidden language of scientific honesty. You see, physics isn't just about finding the final answer. It's entirely about how much we can actually trust that answer. Okay, let's dive into this. The truth is, every single instrument has a limit. Human perception has limits. Even the universe itself puts boundaries on what we can know. Significant figures are really the scientific community's elegant, super practical response to this unavoidable reality of imperfection. Which brings us to a kind of uncomfortable question. Are you lying with your calculator? Look, let's be honest, we all share this habit. You do a calculation, your screen spits out 10 decimal places, and you faithfully copy every single one of those digits onto your paper. But in the rigorous world of science, doing that is actually a form of scientific fabrication. Imagine you're measuring the acceleration of gravity in your classroom with just a simple pendulum and a stopwatch, and you write down 9.8100000 meters per second squared. Writing it this way isn't just mathematically wrong, it's making a really bold, totally false claim about precision that your string and stopwatch simply cannot support. You're telling the world you measure this to a billionth of a degree of accuracy, which is, well, impossible for that setup. Section 1. The language of honesty and measurement truths. We really need to shift how we think about numbers here, because writing down a number in physics is a profound claim about the physical world and exactly how well you know it. So here's the foundational definition. Significant figures are all the certain digits in a measurement, plus exactly one uncertain but meaningful estimated digit. Think about a standard ruler with 1 millimeter marks. When you measure something, you can be absolutely certain of the millimeters, but your eye allows you to estimate just one additional decimal place, maybe halfway between the marks, so 0.5 millimeters. That estimated final digit is your last significant figure. Actually, scratch that. If you try to guess the next decimal place after that, you've crossed the line into straight-up fabricating data. Section 2. Mastering the zero. Placeholders versus data. Zeros are basically the most notorious source of confusion in physics classes. The big question is always, is a zero just a placeholder or is it hard-earned data? If you measure 540, that trailing zero without a decimal point is completely ambiguous. Like, did you measure exactly 540 or just roughly 500 something? It technically only has two significant figures. But if you write 5.40 times 10 to the second power in scientific notation, well, that zero is explicitly significant. You are declaring to the reader, I measured this right down to that exact zero. And this brilliantly illustrates how scientific notation acts as the ultimate clarifier here. To totally demystify the rules, just follow the golden rule of counting. Step 1, start at the leftmost non-zero digit. Leading zeros, they never count. Step 2, count every single digit from there to the end. This ensures you grasp that zeros sandwiched between numbers, or zeros trailing after a decimal point, always carry real information. And step 3, resolve those pesky trailing whole number zeros by using scientific notation. Easy, right? Section 3, the rules of rounding and mechanics, math and physics. Now, it's one thing to record an honest measurement. It's a whole other thing to maintain that honesty when you start crunching numbers. Here's a fascinating, slightly dramatic insider secret used in research-level scientific computing: banker's rounding. You probably learned the standard round half up method in high school. If it's a 5, always round up. But think about it. If you do that across thousands of data points, you create a statistical upward bias. Banker's rounding fixes this completely. When the decision digit is exactly 5, you round to the nearest even number. So 3.75 becomes 3.8, but 3.65 becomes 3.6. It is a brilliant way to eliminate cumulative bias. When combining measured quantities, the math rules literally split depending on the operation. For addition and subtraction, you round your result to the least number of decimal places. But for multiplication and division, you round to the least number of significant figures. Oh, and a crucial reminder here, always keep extra digits during your intermediate mathematical steps. You only apply these rounding rules to your final answer. Otherwise, you'll get some nasty accumulated rounding errors. Because if you aren't careful with those math rules, you can fall into a trap called catastrophic cancellation. So the crucial point is that when you subtract two nearly equal numbers, your precision can absolutely plummet. Imagine subtracting 9.9999 from 10.0001. Your calculator confidently says 0.0002. You literally just went from 5 significant figures on both inputs down to a single significant figure in your answer. It completely masks the lost precision in your data. Section 4, Errors and Uncertainty, Navigating Lab Realities. Bridging the gap between abstract math rules and physical laboratory equipment means dealing with two totally different types of error. Systematic errors cause a predictable shift in your data, like a miscalibrated balance that consistently reads 0.05 grams too high. It destroys your accuracy, and honestly, you just have to fix it by recalibrating. Random errors, on the other hand, are unpredictable fluctuations, like thermal noise in a digital sensor. They scatter your results and ruin your precision. And the only way to combat random error is by a statistical averaging. Why does this matter? Just look at the real-world stakes here. In civil engineering, overstating precision in your structural calculations can lead to totally false confidence in a bridge's safety. In pharmaceuticals, the difference of one significant figure in a drug concentration calculation can mean the difference between a life-saving therapy and a toxic dose. And in climate science, tracking global warming requires extreme precision. The geopolitical and environmental difference between a 1.49 degree and a 1.50 degrees Celsius global temperature rise is absolutely massive. Section 5, From Lab to Cosmos, Scaling Precision. Let's move to and see how this builds, because these exact same rules apply to both mundane everyday objects and the mind-bending extremes of our universe. Our historical quest for truth starts way back around 2750 BCE, when the Egyptian royal cubits standardized length for the pyramids. By 1614, Napier's logarithms demanded we figure out computational clarity, and this all culminates in 2016, when the LIGO Observatory detected gravitational waves by measuring a change in distance of 10 to the negative 18th meters. That is literally a fraction of a single proton's diameter. Incredible. Take a moment to really look at this massive number. This is the Rydberg constant, a foundational number in atomic physics, and it's known to an astounding 15 significant figures. This visually demonstrates the sheer power of human ingenuity at the frontier of quantum optical spectroscopy. Every single one of those digits is a verified, hard-won physical truth about our universe. But then we hit a wall. Now, what's really interesting here is the staggering contrast. This number is the Planck length. Down to this microscopic scale, 1.6 times 10 to the negative 35th meters, the universe simply stops cooperating. Because of quantum mechanics and the uncertainty principle, the very concept of measurement completely breaks down. You literally cannot measure anything more finely than this. It is the ultimate hard limit on precision. Which leaves us with this provocative thought to end our explainer today. If the universe itself has a fundamental built-in limit on precision, what does it truly mean to measure reality? Significant figures aren't just frustrating rules for a high school math test. They are the literal boundaries of human knowledge and scientific honesty. Keep questioning, keep seeking clarity, and we'll see you in the next explainer.